Alright, let's start on this. So given n nodes labeled from 0 to n minus 1 and a list of undirected edges. Okay. Each edge pair is a parent node. Write a function to find the number of connected components in an undirected graph. So essentially, if undirected edges are given, we should be able to go from any place to any place, right? If 0, 1 is given to us, basically that means that 0 and 1 have an edge, and similarly 1 and 0 have an edge. It's kind of like that. Now, we need to just find the write a function to find number of connected components. So to find number of connected components, it's quite simple. So we will DFS from each node. We're gonna maintain a mapping of nodes we have already seen, and maybe we can label them. Every time we start a new, we can just pass that new label. And now so this is a dict. It need not be a dict. In the end, whatever number of labels we have, that's the number of connected components. And now we have done a DFS. For doing a DFS now, so just thinking about these two cases. So this is a simple thing, but to do a DFS, you need to start a number and you need to know all the neighbors of it. So right now, if you need to know all the neighbors of it, you need to first construct an adjacency list. So for constructing an adjacency list, we need to have a kind of a dictionary where we'll have 0 and then list of nodes that is connected to 1 and list of nodes that is connected to 1, so on and so forth. Right, so let's just first convert that. So adjacency list is say a dictionary, and we're going to pass the edges for edge in edges. We're going to do adjacency list. So if edge 0 not an adjacency list, we can also default right from collections import default it, and with this could be a default it of list. Right. So now we can just do edge list of edge edge of 0 actually, and we can append to that edge of 1 and the opposite. Won't exist great, but now we have these things sorted, and this should populate the adjacency list. Once we have the adjacency list, next thing we need to do is do a DFS of our so num of component is 0, or let's say 1, as long as we did get what is n. We have passed n also, which is fine. Okay. Cool. If n is equal to 0, we can kind of return 0. If n is equal to 1, we can return 1. Cannot be more than that, right? If n is equal to 0, 1, and if it becomes 2, it can be two different components also. Yeah. Okay. So num of component for I in range n is gonna pick up node which is I, and now it's gonna do a DFS. So we'll have a DFS function, dev DFS, and it's gonna get node, and nothing it's gonna get a label also, and there's gonna be a scene also. So if node is I, we're gonna for neighbors in node dot, not node dot, it's like agency list node, which is gonna give us neighbors. If neighbors not in scene, we're gonna call DFS with neighbor node. Label is gonna be number of component. Every time we need to call DFS, we have to increment. So maybe we can start with 0. First time when it come up here, it's gonna increment it and send it across. Node seen, let's continue. Because if node is seen, then all its edges would have also been explored already. But if it's not seen, then it's gonna go ahead. It should mark it as seen in that case. So scene dot add node, and in this case, at least this node was not seen before. So this node at least by itself exists separately. So we can safely say the number of components is at least 1. Now we're going to pass the number of components and we're going to pass the scene. Right. And what DFS is going to do is it's going to do the same thing. It's going to check if we're going to add it to in for neighbor in adjacent list node if neighbor not in scene, then it's going to do a DFS of the neighbor. Label is going to remain the same, and scene we're going to pass the scene, and that's how it will go. Let me just mark it here scene. Any node, yeah, and cool. Then we need to just return number of component. Will this work? Will this work? So let's just consider a dry run example because we are only 8 minutes past. We should be able to do a dry run quite fast. So and then we can do 5 here, 0. So our agency list will 0, 1, 2, 3, 4. Right. And 0 is connected to 1. So 0 and 1, 1 is 0, 1 is connected to 2, 1 is 1 gets 2, 2 gets 1, 3 is connected to 4, 3 gets 4, 4 gets 3. Now we are done with adjacency list. This is what should happen here. We have a scene, then we have a DFS, number of components will become 0. So this is 0 for us. We're going to go inside from 0 to 4 and we're going to pick up node as 0, right? And we're going to see node is seen. No, it's not seen. Oh yeah, seen. It's also not there right now. So is node seen? No, it's not seen. Then we're going to add it to scene, which is 0 gets added here. Number of components becomes 1. And for neighbor in adjacency list, which is just 1, we're going to see if neighbor is not in scene. It's not in scene. So we're going to call DFS. So it goes into DFS. It adds it into scene. The number of component remains 1. Number of components is not really required to be sent here in that case, right? So DFS not seen, DFS not seen. Yeah, okay. Now one gets set, one's neighbors get checked out, which is 0 and 2. 0 is already in scene, that won't be picked up. 2 is not in scene, so we call 2 and scene. Now 2 comes up, 2 gets added into scene, and we go into 2's neighbors, which is 1. 1 is already in scene, nothing happens, it returns here. Once it returns, it goes to the next node. 1. 1 gets chosen, if not in scene, we just continue. 2 gets chosen, 2 is also in scene, continue. 3 gets chosen. 3 is not in scene, so we're gonna implement this by 1, 2, and we're gonna pick up 4. 4 goes here, 4 gets added to scene, 3 gets added to scene, 4 gets added to scene, 4 has just a single neighbor 3, that's already there, it returns, number of component becomes 2. Right, seems okay, yaar. Let's just try to run this now. Woohoo! Yes, memory usage is quite bad because we created an adjacency list and maybe a default dictionary. Maybe all that was not required, but it's faster because we are doing a DFS probably. But yeah, this does it. Let's see.